Nice to meet you. I'm Prof.Joun, working for GNU in Korea. The topic of this lecture is on weighted residual method. It is aimed to intensify the practical knowledge about approximation of boundary value problems. Some more details contents can be found from this reference, which is targeted at introducing finite method coupled with mathematics and solid mechanics. I prepared two preliminaries for the weighted residual method. First, recall your memory of a mathematics problem in your high school days. This example is to find the unknowns of x and y, which satisfy this identity equation with respect to W1 and W2. That is, this equation should be satisfied for any W1 and W2. In this case, we have to rearrange the equation with respect to W1 and W2, and then we have to impose zero values on their coefficients, like this and this relations respectively. Then we obtain these solutions. Now, let's go to the second problem, which asks us to find the function out of many cases which satisfy this integration equation but violates this boundary value problem. Because integral from 0 to 1 of sine 2 pi x is 0, differentiation pi double prime plus x squared equals sine 2 pi x satisfies the right integral equation. However, this new boundary value problem is different from this given boundary value problem. Of course, this function satisfies the right side but violates the left side. These two examples may be very helpful for your understanding and expanding your experiences towards the weighted residual method. We can make this integral equation easily from this differentiation. In this equation, omega x is a given function called weighting function. When this condition is not involved, the left problem is the only necessary condition of the right problem. That is, if the left problem is true, then the right problem is also true. However, the right problem does not guarantee the left problem. When this condition is imposed, that is, omega x, the weighting function, is arbitrary, it should be satisfied for all omega x, and thus this should vanish. Therefore, these two problems are identical with each other. Now, we apply the rule of integration by parts to omega pi double prime x to obtain this problem. We can sum without loss of generality that omega 0 and omega 1 are all zeros because essential boundary conditions are imposed on the boundaries x equals 0 and x equals 1. Because you know variance principle, where we have to impose the similar constraint on eta x, you can understand that we can impose some constraint on weighting function like this. As a consequence, we obtain this new problem, which is called weak form. There may be many different approaches depending on the summed weighting functions. Several weighted residual approaches, including Gaultian approach, start from this weak form. In the weighted residual method, we have to apply arbitrary functions for the weighting function to obtain exact solution. A sort of approximation of the weighting function is thus indispensable. There are several well-known approaches to approximate the weighting function. In least square approximation, the differentiation itself is employed for this purpose. There are two collocation methods, that is, point and subdomain collocation methods. In point collocation method, the weighting function is so-called delta function, which makes the approximation meet exactly the differentiation at the selected points, while the latter makes the average value of the error over the selected region become 0. There are also two Galerkin methods, including Dubnov-Galerkin and Petrov-Galerkin. The former utilizes the same basis function employed for trial function to approximate the known function, while the latter does a little modified weighting function, which is denoted by this tilde function. In most cases, Dubnov-Galerkin method is used. To the contrary, Petrov-Galerkin approximation is employed in the case that the differentiation contains a term with odd order. First, let's calculate a least square approximation using this trial function. We can start from the weak form, but let's start from this problem to emphasize the equation form of least square approximation. After simplifying the problem in infinite-dimensional function space to the problem in two-dimensional vector space, and applying the necessary condition for this function to be extremum, we get this matrix form of the linear equations. Solving these equations for two unknown constants and applying them in the trial function, we obtain this approximate solution. This figure compares the approximation with the exact solution, indicating that the error is a bit bigger than the reached approximation, even though we minimize the error function of the differential equation itself by the least square approximation. This method is relatively ineffective compared to Ritz method. And it should require a higher order polynomial for the trial function, even though it can be used for any boundary value problem. Now let's solve the approximation problem by two-point collocation method. The problem is formulated like this. When we employ this trial function, we can obtain very simply this relation for any selected point. Of course, integral function multiplied by a delta function, delta x minus xi, is the function value itself at x equals xi, because delta x minus xi goes infinite, but its integral at that point is unity. Yes, the calculation in this approach is quite simple, but it's unfortunate that the resulting matrix is unsymmetrical, and that the higher order of polynomials that are elements of second sovereign space should be used. The solution looks good from this comparison with the exact solution, but compared with the risk solution, we have to remember it is a little worse. Let's study an example of Galerkin, that is Bubnov-Galerkin approximation. When we use these trial functions, that is, a linear combination of basis function x 1 minus x and x squared 1 minus x, we have to apply the basis functions for the weighting function in the Galerkin approximation. So we obtain these two linear equations, applying them to this weak form. They can be expressed in a matrix form where the matrix is symmetric. Solving this linear equation and plugging C1 and C2 to this trial function, we obtain this approximate solution, which is the same with the recent approximation. So comparison with exact solution was skipped. The same problem can be solved by Gaultier method in a slightly different way. Of course, the basic principle is the same. When we assume the trial function like this, we put its corresponding weighting function as a linear combination of the same basis function employed to define the trial function for a known function. W1 and W2 should be indispensably arbitrary. Plugging these two approximated functions to the weak form, we obtain this identity equation with respect to arbitrarily constant W1 and W2. Therefore, we obtain two linear equations because the coefficient of W1 and W2 should be all 0 in this kind of identity equation. Of course, the solution is the same with that in the previous slide. Let's use a special trial function that can depict the exact solution to check what happens in the Gaultier method. Plugging 1 over 12, 0 and 0 for C1, C2 and C3 to this trial function respectively, we obtain the exact solution of this function. It is thus concluded that this trial function can depict the exact solution. Thus it is special. Substituting these two approximated functions into the weak form, we obtain this set of three linear equations for three unknown constants. Of course, we obtain 1 over 12, 0 and 0 for C1, C2 and C3 respectively, indicating that we obtain the exact solution when the linear combination of basis functions can express the exact solution. Now, let's generalize the approximation method based on Gaultier approximation. We assume the unknown function as linear combination of n independent basis functions. Note that the resulting matrix becomes singular when the basis functions are dependent. In Gaultier approximation, we assume the weighting function as a linear combination of the same basis functions. Note that a little modification may be sometimes needed to make the linear combination satisfy with constraint imposed on the weighting function. All double i's for the approximated weighting function should be arbitrary, and thus we obtain an identity equation with respect to the double I, like here. Therefore, this term for any I should be 0, and we formulate n linear equations for n unknown constant. The linear equations are usually expressed in a matrix form like this, by a stiffness matrix and a force vector, which are defined by these relations. We use these terminologies, stiffness matrix and force vector, regardless of the kind of engineering problems. Of course, the matrix is well-natured, that is symmetric. It is also non-singular if the basis functions are linearly independent. Now, let's look at a boundary layer problem involving a natural boundary condition like this at x equals 1. The other conditions are the same with the previous problem. Now we can construct this problem, which is the same with this given problem, under the condition that omega x and omega bar x are arbitrary. Omega bar 1 is thus an arbitrarily constant. Applying integration by parts to deduce the maximum order of differentiation in this integrand, we obtain this equation just before some constraints are imposed on the weighting function. You'd better know that the maximum order of differentiation in the weak form reduces to p when its corresponding differential equation is of 2 times p order. Now we'll sum omega 0 equals 0 and omega bar 1 equals minus omega 1 without loss of generality. I hope you to try to understand by insight this assumption process from the same process in Ritz method. In the Ritz method, however, we don't need any assumption, and it is mathematically perfect. That's why we study first the Ritz method in spite of its defect in terms of generality. Finally, we obtain this weak form. You can see that the natural boundary condition disappeared. This is little great in terms of approximation. If a trial function satisfying natural boundary conditions is needed, the difficulty of approximation may tremendously increases. Anyway, it is very lucky that natural boundary condition disappeared with this remaining left inside the integral equation in the weak form. We don't thus have to consider the natural boundary condition at all when preparing the trial function. What we have to consider is only the essential boundary conditions that can be easily accomplished by FP approximation, that is interpolation function, which will be studied soon. Of course, to find the trial function which meets only the essential boundary conditions of actual engineering problems on 2D plane and in 3D space is almost impossible without any technique like FE approximation. It had been the problem of conventional theoretical approximation methods of boundary layer problems for the sake of engineering application. Let's calculate an approximate solution using this trial function for this problem. Of course, this trial function should satisfy only these essential boundary conditions. We have to use the same basis function for the weighting function. Applying these two approximated functions to the weak form, we can derive a set of 3 linear equations which gives us this approximate solution. This figure compares the approximate solution with the exact solution. You know, solid line is usually for the more important one, and I used purposely the solid line here for the approximate solution because it is more important in engineering. Finally, we'll better check the accuracy of the solution with emphasis on natural boundary condition. The exact value of phi prime 1 equals 1, of course because it was given. Phi tilde prime 1 equals 79 plus 12 minus 30 over 60. Okay, that is 61 over 60. Of course, it is not exact, as the function of the approximation is not exact. That is, the approximation is a third order polynomial, and the exact solution is of order 4. We can say that this weak form considers the natural boundary condition as well as the differentiation in the process of optimizing the solution in its original way.